At this point, we've learned a bunch of facts about gravity. In this tutorial, we're going to step back a bit and relate all those facts in order to better understand gravity in a bigger picture. Not only will this lead to a better understanding of the force of gravity, but it'll also make it easier to remember all those facts, as they'll make a lot more sense when they're all related. Our first look at gravity was in kinematics, or the study of motion. We were dealing with acceleration problems, and we recognized that one of the most common causes of acceleration is gravity. So, how do we give you the tools to solve some kinematics problems involving gravity when you don't yet fully understand forces? Well, we can get around that by telling you that near the surface of the Earth, gravity causes free-falling objects, or projectiles, to accelerate towards the Earth at minus 9.8 meters per second squared. And off you go. You have an acceleration, so you're able to solve a variety of real-life problems, not really understanding where this minus 9.8 meters per second squared came from, but still able to solve some really good problems. Now, most recently, you've learned about forces. Then, the force of gravity in a very general sense, that is Newton's general gravitation equation, Fg equals g m1 m2 over r squared. Now, this equation allows us to determine the magnitude of any gravitational force, as it isn't limited to the surface of the Earth. In fact, this equation works just as well with orbiting planets and asteroids as it does with falling apples and bridges, buildings, and anything else along the surface of the Earth. So, we should be able to start with Newton's general force equation and use it to determine where this minus 9.8 meters per second squared came from. Let's approach it this way. The majority of designers, that is physicists, engineers, technologists, etc., have to consider the force of gravity in their designs regularly when they're designing cars, boats, planes, bridges, buildings, etc. What's the most common thing about all these calculations that are happening is that the majority of them are along the surface of the Earth. So, certainly, we could use Newton's general gravity equation for their calculations. It's the general equation, so it works anywhere, right? So, let's do an example. If they wanted to determine the force of gravity between a person and the Earth, they'd use the constant g, that really small number. If we say that mass 1 is the Earth's mass, that's fine. Then mass 2, now that would be the person's mass, so let's just push it over to the side here. Now, r is the distance between the centers of mass. Now, if we look closely at r, we know that it's basically the radius of the Earth plus just a little bit more. That is, if you were 2 meters tall, your center of mass might be a little over 1 meter. With the radius of the Earth being 6,371,000 meters, the extra meter makes no significant difference. Even if it were 100 meters or 1,000 meters, change in r, well, it's still less than 0.15%. It's basically the radius of the Earth. So, a smart designer might be inclined to stop and say, why the heck do I keep plugging in all this same information into my equations when I'm calculating the force of gravity? The g is always the same. Of course, it's a constant. The mass of the Earth, well, that's always the same too. And the distance r is always, well, basically the same as we discussed. It doesn't change any significant amount. Perhaps we can simplify all of this into something easier to work with. since we're dealing with the same calculations near the surface of the Earth, and all these are basically the same, let's put them all together and we'll just pull the only thing that changes out. That is our mass 2, or we'll just call it m. Now, what do we have left when we put all these others together? Well, we pull out the calculator and calculate them, and we come out with a number 9.8 meters per second squared. Now, to make things easier for future calculations, we may say, well, let's just give this number a name so that we can pull it out, and any time we're doing a force of gravity near the surface of the Earth, rather than using the general equation, we'll just take the mass and multiply it by this other number, and we can have it very nice and quick. Let's call this other number little g. Lo and behold, we have a new equation. Fg equals m little g. A much simpler equation than our general formula. This will make calculations much easier, and if we're talking about items near the Earth's surface, any error will be negligible. Of course, the error will increase as we move away from the Earth's surface. That is, the r gets much bigger than the radius of the Earth. But really, the error is acceptable for common design calculations at the tops of buildings and mountains and even in most planes. Once you're talking about satellites and rockets, though, well, then the distance r gets significantly different than the radius of the Earth, and we definitely have to go back to our general equation. Given that, when we're working near the surface of the Earth, which is most often the case, we'll cheat, and we'll bypass the need to plug in all those other values. We'll just use our Fg equals m little g, with g equals 9.8 meters per second squared. The only caution is that we have to remember that this is an estimation, and it's based on being close to the surface of the Earth. Don't forget this and start using this estimation for satellites and rockets or planets. The general equation is still the best one.